Right, so I'm Julien Le Kernec. I'm with Glasgow Uni, I'll be giving you a small overview of radar sensing in assisted living. So obviously I don't work by myself. There are a lot of students and staff associated with this project. So these are the results coming from Glasgow Uni, University Cergy-Pontoise in France. A bit of Nanjing University of Science and Technology, TU Delft, and also UESD, I forgot to put in there. So first, assisted living. Why is this important? Well, we have a global aging population, and in some countries more so. This is actually the projections for the population in China. And by 2050, they will have a major problem with an elderly population, with 1/3 being over 60. And that's why they've introduced, for example, the 3-child policy, whereas it was one not so long ago. So it's not just China. I mean, it's all over. We have a problem with aging. So a lot of governments are shifting towards maintaining people at home longer and shifting care from primary care units to community care, GP practices, and ultimately to the home. So people are living longer. They want to live healthier, have a better quality of life. So there's also an interest in tracking and also for safety in case of a critical event happening, like a stroke or a heart attack or just a fall. Okay, so this is kind of the context of why we're looking at assisted living. So the concept is actually to ultimately is to have sensors within a living unit, collecting data on what's happening in the home, processing, classifying the signals. So at the beginning, we want to target activities of daily living. And this is mostly because those are the 6 activities you're supposed to be doing independently to survive at home. Okay. And I mean, survive and not live. For living, you have extended activities of daily living. Adjusting that already is complicated enough. Furthermore, I'm not going to talk about this today, but you can also look at vitals, collecting information about heart rate, breathing rate, blood pressure, and other things, at the same time. And collecting the two together allows you to actually derive trends and also infer information on the person's health. So assistive technologies are not new. There are a few players in the field already in terms of technologies that are currently deployed, but still presenting some challenges. So cameras, if you look at classification, etc., they're actually quite advanced. If you look at the field of vision, for example, but they pose problems in terms of privacy. And this is a major concern. So even though it would work pretty well, this is actually not something users or regulators want to see being deployed. Wearables, again, the technology is quite mature, works quite well. The only problem with it, it needs to be worn. And when you think about the target population, which is actually the elderly, they can have cognitive problems and just not be able to remember to do this, or just simply forget. And commonly, accidents do happen at night. For example, if you go to the bathroom or something, and then accidents happen and you have forgotten to put your wearable on, and it's useless. You also have ambient sensors, like acoustic and PIR. So acoustic has the same problem as cameras. It's perceived as an invasion of privacy. And PIRs are actually quite well accepted, but they provide very coarse information. Smart floors are a nice option as well. The issue with this is actually cost, and the fact that you need to remodel your entire apartment to fit them in. So I like this graph here because this is something we need to remember when we develop technologies for the public. That it's not developing tech just for the sake of technology, but also we need to take into account user acceptance. So here is a graph of presenting different sensing modalities with, the richness of information on the ordinates and the perceived privacy from the user on the abscissa. And you find cameras over here, smartphones are right there. You can perceive privacy is rather rather low, but people sort of accept this. You already volunteer quite a bit of your data, but a lot of you already have Wi-Fi at home, and radar is not so much different. So that's why I think like radar provides you very rich information in the same range as visible video, and at the same time, because this is a radio technology and you cannot see directly visually what's happening, and this is something that would be quite well accepted. So why radar for assisted living? So essentially has a multitude of benefits compared to existing techs. No reliance on user acceptance or compliance. No need to carry your attached devices. You don't have identifiable data unless you use quite complex algorithms to do this. And you don't need to remodel the environments to install the sensors. So, and here you have a small example of what we have available at Glasgow Uni to play with. And we're also developing bespoke platforms for this as well. So in terms of human activity recognition, what's being done in 99% of publications, I'm probably exaggerating, but there's probably very close to that. People use micro Doppler. So are you all doing radar in this audience, or do we have people from other backgrounds as well? Just to know where I put my explanation at.
I think most people here do have backgrounds in radar, and most people here are working in that.
Okie dokie. Well, then so I can just say micro Doppler, and you already know exactly what I'm talking about. That's brilliant. So here you have one micro Doppler signature. So here this is for walking, and it comes from one of the Anchor Tech platforms. And you obtain this through different time frequency transforms. But this one is with FFT, but you could use bilinear transforms or something to try and optimize this. Although some recent studies have shown that using the FFT is still the most efficient that was used to date. So FFT is simple, it works, it's efficient. You get a lot of information from micro Doppler, and you can extract a lot of features from that, and then classify with various various classifiers, from statistical learning to deep learning, and even more complex, architectures now. So in most cases, the activities that are presented are quite easy to distinguish just from the micro Doppler signature. Now, if that's the case and you can already do it by eye, your classifier is going to have a very easy time to do that. Now, if you design activities that will be easily confused, if you just look at the speed, then you get into trouble. So I've labeled those micro Doppler signatures here, and you can see that, if they were not labeled, it would actually be quite hard to distinguish this one from that one, or sitting from standing, or tying your shoelace from a frontal fall. You can see that the frontal fall is actually quite a critical event, whereas tying your shoelace is kind of benign. And generating a false alarm because someone is tying his shoelace rather than having a frontal fall and dispatching emergency services could be a problem. So we actually have to extend our field of view here of the different radar data domains that are available. So, you have raw data that you can exploit. So the trade-off you have here, if the further you go into producing your radar data domains, the more pre-processing you will need before you classify the data. Whereas, the earlier, if you take, for example, the raw data directly, this is going to make your classification algorithm rather large compared to, even just one step after using the range type data directly. So there's quite a lot of work now trying to fuse information from those different data domains to try and improve the accuracy. So I'm opening a can of worms here rather than giving answers. So there's still a lot of work being done and needing to be done here. From what's the best way to combine data domains and to have a good trade-off between pre-processing and classification accuracy here. But those that are emerging in terms of representations, actually 3D representations, combining range, Doppler, and time in the same representation, and that requires 3D, or you could actually have like NPCA here for feature extraction, and that also leads to rather complex classification architectures there. You can use some projections to try to reduce that to 2D afterwards, once you've extracted the features. But again, that requires more transformations and everything, but those give good results. You also see some new things emerging. So from the thesis of Rodi Gendel, he's in TU Delft working with Francesco. So he's worked on the radon transform from the range type data to try and distinguish activities. And I'm currently working on a new data representation derived from telecommunication using cyclostationarity. And we'll probably have primary results, preliminary results on this in the next IRC conference in Hainan, I think, this year. So as you can see here, you have a multitude of data representations that can help you get more information to try and distinguish between activities. So which one to use, which features to use, which algorithm then to use to classify or extract data automatically. Your guess is as good as mine. Keep exploring, keep working at it, and we'll get there eventually. But that's a very interesting topic there, and there's still a lot to do here. So in terms of this, I mentioned this just a second ago, but the AI topology is starting to become very important. Simply because I've mentioned at the beginning that you have different assistive technologies. So there will come a time where you will have to combine or fuse the data from those different sensors together. And those sensors might be distributed within a home environment. So there will be a question of, if you have several radar nodes, then how do you combine the data together? And also, if you have data coming from other sensors working at different data rates, again, how do you combine those together? And most importantly, you will have to communicate this information, coming from the sensor to maybe a centralized unit or an edge platform or something. So the question now comes, on, how much pre-processing do you need to be doing on the sensor, well, near the sensor, at the back of the sensor, and do you need to start classification and do everything in only communicated decision, or do you do some of it there, communicate in the middle, and then continue the classification or some of the pre-processing after on the edge platform? Those will be design choices. You might also need to compress the data for transmissions, to optimize the communication load, because communication over a wireless channel or even wired, you may actually find a bottleneck of communication if you have a lot of IoT devices in the one place. So a second aspect of the AI topology is trying to minimize as well the number of hyperparameters. One, that would be to reduce training reduce training time, reduce the number of hyperparameters to look at, and being able to reuse the different layers at the back of similar sensors. Again, if you're putting different nodes in or new nodes in, then that makes it easy to increase the number of sensors in your living unit. Another problem with radar at the moment, and do provide a nice database for you to play with, but it's the size of the data you have to train on. With deep learning, you need a lot of data to be training on, and having algorithms actually generalize quite well based on a small amount of data is quite good. I think those results are coming from a paper from Gangley in 2018, or 2018, I think, or 2019, on personal recognition. There was a very good architecture there that still works quite well. But you now have other AI topologies, like with zero-shot learning or one-shot learning, that are interesting alleyways to explore to try and solve those problems, to have models that generalize with a minimum amount of data, or have algorithms that learn over time. Because one key advantage of using machine learning, assisted living and one living unit, is you want the algorithm to actually overfit the person that is living there. You want this algorithm to actually specialize to recognize activities from that person. But then you can also imagine every household having one model for classification, for individual X, individual Y and Z, and then update those local models from a meta model that learns from all those different models coming from different households, and have some sort of federated learning approach there to improve the algorithm and the generalization to learn new things as it goes along. So other open challenges in this particular area is actually the challenge of real time. So I mentioned multi-data rates for sensors. So GPUs are quite good for fast implementation, but they don't deal very well with multi-data rates in data. So you need to tweak your data a little bit to be able to process it on the GPU just by multiplying the amount of samples you have in one, or equate things somehow before you start classifying. Whereas FPGAs are actually developed so that it can accommodate massively parallel computing, multiple data rates. It's built for this, and it's also more energy efficient. And you have rapid prototyping for pre-processing, and also machine learning has been rolled out since last year, on the Xilinx with the DNA library engine for Alveo that allows you to prototype your algorithm directly on those platforms. So we have a PhD student in France who's starting in October. They will look at embedded processing and the limitations of the algorithm and implementation for what needs to be done and looked at, because if we want this to be deployed in a home environment, we need to look at embedded processing, and there are a number of issues there. One of them being handling fixed precision or half precision floating point calculations and all the errors they carry, while maintaining the same level of accuracy for recognition. Another aspect, in something that's not looked at very often in human activity recognition with radar, is the aspect angle. So this is the monostatic signature of a person jumping at 0, 45, or 90 degrees. And you can very much see that if you train an algorithm on this is not going to be able to recognize a jump at 90 degrees. So we need to be developing algorithms that algorithms also look at the hardware to try and recognize activities at any aspect angle, because people will walk in different directions. So in a paper we've actually published just in April, I think, we've looked in simulation at monostatic, multistatic, and interferometric implementations of radar. So interferometric, you correlate actually the data from two receivers and then integrate, and this is your interferometric channel. So for the same activity here, you see at 0, 45, and 90 degrees, the signature increases. Okay, that gives you information about the rotation of the target in your field of view there. And what we have shown is that the interferometric implementation has an overall better performance across all the aspect angles from 0 to 90 degrees, whereas for monostatic it starts going down after 30, 35 degrees. Multistatic circular after 40, 45 degrees as well, but a bit further than monostatic, and then multistatic in line it starts degrading after 60 degrees, but I didn't have enough room there to show it. You'll find all the details in there. It's quite a detailed analysis there with different performance for individual activities as well. So now it needs to be validated experimentally. So I now have a radar to do this. Just need to do a few experiments with that and a new database to validate this. So it's going to take a bit of time. Finally, as my last slide after that, I'll give you back the floor because I don't want to be, no, actually just on time, 30 minutes. What solutions are, for continuous data stream? So that's the next frontier, I think. And for continuous data streams, there are like 2 dimensions. The first one being, how to segment a continuous data stream to recognize individual activities. So there's a lot of work to be done there. And the segmentation needs to be automated and adaptive. But segmentation there, is for time, but also we need to be able to extract automatically regions of interest. And here, I give a couple of examples of what you can be doing here. And with a binary mask, extracting the amplitude or the phase, based on the binary mask here. So I'm talking about phase because phase, I think, is going to be very important in the future of what we're developing. So we need to be developing classification algorithms that are native to the data format of radar and not rely solely on vision algorithms because our data is complex by nature and it's not just pixels of luminance in red, green or blue. So this is very important, and we've shown some of our publications that just incorporating phase when you're fusing data actually accelerates training quite a bit. So consider this for your next implementations. And that's me. Thank you. And I think that's 30 minutes roughly, or 25, or